Teacher Carlos Plain of Durham School states, "Definitely. I went through my entire time on Earth empowering a specific theory of the universe, and eventually the hypothesis is being attempted. I welcome that, since that is the way we push ahead. That is the means by which we make strides in science." The James Webb Space Telescope is upsetting a lot of what has been seen as truth in cosmology for the new years. Another ultra-deep picture shows that we have committed mistakes in cosmology. The telescope that should show us the fundamental stars of the universe is changing into a foe of the previous perspective and may present to us an outright different science. Not all examiners are groveling in dread at the new realities. Different experts invite the advancements, since it has for quite a long time been certain that something was the matter with our old speculations. The distortion in the evaluation of the expansion speed of the universe alone should have shaken specialists' comprehension at some point in the past, yet taking everything into account, they complied with old speculations. The vast microwave background radiation, CMB, considered the most settled light known to man, was made around 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to form stable hydrogen particles. Scientists call this progress reionization, which made the universe vulnerable to light. The CMB was first seen in 1964 by American physicists Arno Penzias and Robert Wilson while they were dealing with another kind of radio receiving wire technology. This discovery was, for a long time, seen as possibly the strongest piece of evidence for the theory of how things came to be, earning Penzias and Wilson a Nobel Prize and an evidence spot in the history of astronomy. The CMB probably offers a survey of the early universe, with little temperature differences giving critical data about the circumstances not long after the Big Bang. Researchers involved the CMB as a solid carving of the major assessments of the material universe to check the expansion speed of the universe, among other things. The astronomer Edwin Hubble had previously settled this in the late 1920s, finding that distant, vanishing structures retreat from us in every direction and that their speed is contrasting with their distance. Today, these observations are known as the Hubble law or the Hubble constant. Hubble didn't have the high-level evaluating methodologies available many years later when the CMB was discovered, which led to a recalculated expansion rate generally lower than Hubble's initial figure. Later, researchers recalculated the rate again, using type Ia supernovae as standard candles, giving stable light that could be used as a reliable measuring point. The evaluations within the CMB yielded a growth speed of around 67 kilometers per second per megaparsec, while evaluations using supernovae yielded around 74 kilometers per second per megaparsec. What does this discrepancy in determining the expansion speed of the universe truly tell us? Did you know that this error has been known since the 1990s? Since then, scientists have known, or at least suspected, that something might be the matter with the assessment of the CMB, the evaluation procedures, or the concept of the universe's expansion. The inconsistency between the different surveyed expected values of the expansion rate is referred to in science as the SAA pressure or the Hubble tension. The ramifications of this strain are enormous, demonstrating how basic parts of how we could unravel the universe may be flawed. For years, specialists were puzzled. Since the James Webb Space Telescope went into operation, it has provided investigators with astounding data that may now uncover information on the issue of the expansion speed of the universe, with systems so old and mature that their development should theoretically have started before the Big Bang, disrupting old cosmology. Scientists no longer discuss errors or evaluation differences. They now discuss the greatest crisis in modern astronomy. Besides, not only could the expansion rate be off track, but the entire concept of progression, or the Big Bang itself, is being questioned. Associations of images provide evidence of a universe completely different from what we have long thought. The SAA pressure was the main critique of specialists who still believe in old speculations. Now, they face a dilemma. Do we truly have much knowledge of a universe? Other researchers stand on the remnants of their beautiful source of both gift and torment, examining space with awe, wrestling with what they find. Considering the crisis in science, we should ask ourselves, what do we truly know about the universe? To answer this, we need to understand how science functions. Hypothetical researchers use a complicated combination of mathematical models, careful data, and logical reasoning to move from the general to the specific. Their understanding comes from a blend of observed phenomena, preliminary results, and speculative evaluations. The term theory alone shows that these are constructs and ideas, not outright pieces of knowledge. The only plausible information we have are the photographs telescopes give, the sound waves and radiation gathered with radio telescopes, and the latest information from neutrino surveying systems or gravitational wave detectors. With the James Webb Space Telescope, we now have an instrument that can isolate the most spread-out light into individual frequencies and analyze it in magnificent ways. Webb can show us the ancient parts of distant galaxies from billions of years ago, how much mass they contained, and how many stars were in those areas. It can also trace the shape and course of a galaxy's development. Webb can, however, have limitations. For instance, it can't always definitively determine whether we are seeing galaxies or black holes with massive accretion disks that shine as brilliantly as a galaxy. We must face the truth that our science has long entertained too many possible outcomes as encounters and dismissed alternative explanations. Research has, for a long time, been confident in its precision. The latest discoveries from the James Webb Space Telescope are crucial clues to replace speculations with new insights. As has happened often in science, investigators are now eagerly awaiting new exposures that are unexpectedly surprising, and some scientists are struggling to formulate new explanations. The new revelations shake the foundations of our accepted science, disturbing many specialists. The current models of real science are still often based on Isaac Newton's evaluations from the 17th century. His laws of motion and gravity were the cornerstone of our understanding of this reality and the universe for many years. Newton's rules made sense of the movements of things under normal conditions and worked extraordinarily on Earth. However, in space, his thoughts needed expansion, which was largely provided by Albert Einstein at the beginning of the 20th century. Einstein's groundbreaking theory of relativity, published in 1905, revolutionized how we interpret reality, showing that they are relative to one another and depend on the observer's motion. His general theory of relativity, published in 1915, expanded this idea with mathematical confirmations of gravitational anomalies, considering the curvature of space-time by masses like stars or galaxies. Einstein's rules and ideas were groundbreaking in different areas, but he also understood their limitations. He knew that his theory could never fully describe the universe and longed for a unified field theory, which he never achieved. No other trained professional has managed to solve that puzzle, but it still remains. Wouldn't it be fascinating to know where that next step lies? Michio Kaku, an eminent astrophysicist from the USA, said in an interview that tackling this issue would undoubtedly win a Nobel Prize. Could we investigate whether the experts could have overlooked possible misunderstandings, or whether our telescopes are to blame? Dark matter and dark energy are at the top of the suspect list for the true reasons behind the cosmological crisis. Our evolving models of the universe combine ideas that dark matter and dark energy make up around 95% of the universe, but neither has been clearly observed and their asserted presence has never been proven. They may not exist at all, requiring different explanations for the universe's expansion and the mechanisms of galaxies. On the other hand, they could have properties we don't yet understand. One thought is that the actual properties of dark matter and dark energy have changed over time, possibly showing some form of evolution. Gravity is another solution to be clearly explored. This force, inducing attraction through mass or bending in space-time, has not yet been clearly delineated. The theories of space-time curvature mostly originate from Einstein and have been confirmed many times, but we can't rule out the possibility that gravity has unexpected properties different from what we thought, or that another force causes the gravitational pull between objects. Over time, several constants have been established in cosmology and astronomy. The study of the universe has always been a journey, defined by our relentless pursuit of understanding and discovery, from ancient human civilizations observing the stars to current space telescopes testing the depths of the universe. Every advancement in theory and technology has revealed new secrets while challenging established beliefs. In the field of cosmology, the James Webb Space Telescope, JWST, stands as a beacon of our scientific progress, promising to change how we interpret the universe's origins and development. Launched with remarkable capabilities, the JWST represents a leap forward in observational space science, designed to peer further into reality than ever before. With its advanced infrared technology, the James Webb Space Telescope is poised to answer questions that have eluded astronomers for centuries. Its ability to observe distant galaxies, detect the first stars, and investigate the origins of cosmic structures allows scientists to explore the universe in unprecedented ways. In doing so, it promises to reshape our understanding of the cosmos and perhaps rewrite parts of cosmological theory that have been in place for decades. Webb's instruments allow it to peer through cosmic dust, revealing regions of space that were once hidden from view. It has already provided astronomers with images of the universe's earliest galaxies, some dating back to just a few 100 million years after the Big Bang. These discoveries may offer new insights into the formation of galaxies, the growth of black holes, and the role of dark matter in shaping the structure of the universe. One of the most exciting aspects of the Webb telescope is its ability to study exoplanets, planets outside our solar system. By analyzing the atmospheres of these distant worlds, Webb may help us determine whether they could support life. This could lead to groundbreaking discoveries about the conditions necessary for life to exist beyond Earth, and perhaps even reveal signs of alien life. Yet, despite these advancements, the discoveries made by Webb raise as many questions as they answer. Some of the new data contradict existing theories about the formation of galaxies and the behavior of dark matter. These discrepancies could prompt a major reevaluation of current cosmological models and force scientists to develop new theories to explain the data. The implications of these findings go far beyond the realm of astronomy. They touch on fundamental questions about the nature of reality itself. What is the true structure of space-time? How do the forces of the universe interact with each other at the most fundamental level? How did the universe begin? And what is its ultimate fate? These are the kinds of questions that scientists hope to answer with the help of the James Webb Space Telescope. As we continue to probe the mysteries of the universe, we must also acknowledge the limitations of our knowledge. While we have made incredible strides in understanding the cosmos, there is still much that remains unknown. The history of science has been marked by paradigm shifts, moments when new discoveries forced us to reconsider everything we thought we knew. The work being done with the Webb telescope is likely to be a key part of the next such shift, challenging long-held assumptions and pushing the boundaries of what we can comprehend. In the end, the pursuit of knowledge is a never-ending journey. The more we learn about the universe, the more we realize how much there is still to discover. The James Webb Space Telescope represents just one step in this ongoing journey, but it is a step that may lead to revelations that will redefine our understanding of the cosmos for generations to come. As we continue to explore the vastness of space, we are reminded that the universe is full of mysteries waiting to be uncovered. Whether or not we will ever fully understand its origins, its vastness, and its future, the quest for knowledge will undoubtedly continue, driven by the same curiosity and wonder that has always propelled humanity's exploration of the unknown.